guys, in this video we're going to go over how do we find the resistivity of a wire. Okay, so what we're given here is the length of the wire, its diameter, the potential difference across its ends, and its current. But before we go into this, we're going to go over what is resistivity. Okay, so resistivity is the property of a material. Okay, so different materials will have different values of resistivity. Okay, it tells us what the material is made of. So again, to calculate the resistance of something, it's going to equal its resistivity, the property of the material, times by its length, divided by its cross-section area. Okay? So what we're saying is here is resistance is directly proportional to length, right? We already know that. Because if we have a longer wire compared to a shorter wire, this is from your GCSEs, a longer wire is going to have a higher resistance. We know a longer wire is going to have a higher value of resistance because, again, from a longer wire, we're going to have more of those metal ions locked in place. So when the electrons try to move through, we're going to get more collisions. Right? So there's more collisions between those free electrons and those metal ions locked in place because we see it's got a further distance to travel, loads more collisions than in that shorter wire. Just to recap again what I said, we know wires are solids. So you know from way down lower school to draw solids, we draw particles in a regular arrangement that are all touching. But because it is a metal, we know what's going to happen is we're going to have those metal ions and we're going to have those C of delocalized or those free electrons. So then it's those free electrons that are able to move through that conductor and carry charge. Okay? Just a quick revision again of why metallic bond is like this. Let's imagine you had lithium on your periodic table. So lithium on my periodic table tells me that bottom number is 3 protons. 7 minus 3 is 4 neutrons. And because it's an atom that's neutral, it's going to have equal numbers of positive protons and negative electrons. So what I'm saying here is when we draw this atom, you've got your 3 protons and your 4 neutrons in its nucleus. Let's say about GCSE, we draw 2 electrons in its first shell and it's 1 electron in its outer shell. So lithium, remember, to become stable, is going to lose that outer shell electron. So we get left with those lithium positive ions because we lose a negative electron. If we get rid of something negative, we become more positive. So you can see what this metallic bond would look like is we've got our lithium positive ions, and every lithium positive ion gave away 1 free electron that is free to move there and carry that charge. Okay, we can also see that the resistance is inversely proportional to the area or the cross-sectional area. That makes sense because if the area is really big, we're going to get the resistance to be really low. Okay? If we have a really large area wire versus a really thin wire, the large area wire is going to have a lower value of resistance. And again, it's because there's more space for those electrons to move through, so there's going to be less collisions. You think about this about water flowing through a pipe. It's much easier for water to flow through a big, thick pipe than that water trying to get through that narrow pipe. Okay, so the same thing with resistance. A larger area wire is going to have a lower resistance because it's easier for those electrons to get through. Okay, we can see resistance is proportional to the resistivity. Okay, so what we're saying is here, the lower the value of the resistivity, the lower the resistance. So hope you're thinking if that's the property of a material, the lower the resistivity, the lower the resistance. Clearly, things that have really low values of resistivity are going to be things that are good conductors. Okay, so things that have low values of resistivity are probably things like our copper that we make our wires from. And things with high value of resistivity, which are going to have a high resistance, are things like our insulators. So how does that work, right? So conductors, what happens is we say this valence electron. So valence just means like outer shell, okay? So here, this will be my valence electron, that outer shell. So what we can draw is we can just imagine them like bands. So imagine this is all my valence band with all my outer shell electrons in it. In a conductor, we have this thing called a conduction band. So we're just going to imagine if it's in the conduction band, it's just a region, an area, which means the electrons are free to move and carry that charge. So in a conductor, the valence band and the conduction band, you can see they overlap, right? So all of those valence shells electrons can go into that conduction band, and that's why they're really good at being conductors. There's loads of free electrons. You might think about a semiconductor. So a semiconductor is something like your silicon, okay? So a semiconductor, how it works is there's a gap between the valence band and the conduction band, okay? So again, if I want things to conduct electricity, I need electrons to be in that conduction band. But right now, my electrons are all in the valence band, right? My electrons are down here in that outer shell. If I want my electrons to get into the conduction band, for semiconductors, we have to supply energy. I have to supply energy to get the electrons to move up into that conduction band. So one way we can supply energy is that we can heat it up. So what we were thinking, if I heat something up and it becomes more conductive, if I heat it up and I supply energy, I'm supplying energy from those electrons to move from the valence band into the conduction band. I'm putting in energy. What component do you know about that when you heat up, it becomes more conductive? And that's when you're thinking about your thermistors. So remember, a thermistor, we know, works when the temperature is high, the resistance is lower. And that's because thermistors are made things of semiconductors. When we increase the temperature, we're supplying energy to the electrons in the valence band to get into the conduction band. There's more electrons in the conduction band, so they become better conductors. So the resistance is lower. And then your last thing is things like your insulators. For your insulators, the valence band and the conduction band are super far apart. So that's why it's really difficult to get any of those electrons from that valence shell into that conduction band. You need a really high potential difference to make an insulator conductor. It's kind of like when lightning happens. Okay, so now we know about resistivity. We're going to think about how to calculate resistivity now. So if I want to calculate the resistivity, we can just rearrange this equation. So to calculate resistivity, we're going to do resistance times by area divided by the length. Okay, so now I have to see what I have in my equation. So I don't see resistance anywhere, but I can see I've got potential difference and a current. And I know V equals I times R. So the potential difference, which is 0.2, is equal to my current, 0.4, times by my resistance. So to calculate the resistance, which is 0.2 divided by 0.4. My mental math is shocking, so just use a calculator. 0.2 divided by 0.4 is going to give us 0.5. I could have done that easy. Shame on me. So my resistance there is going to be 0.5. So that's why here I can write resistivity is equal to 0.5 times by that cross-sectional area. So V equals IR, 0.2 divided by 0.4 is 0.5. And we said now we're going to calculate the cross-sectional area. Okay, it told us it's a wire. You have to imagine a wire is normally a cylindrical in shape, right? That's normally my wire. So if I want to find the cross-sectional area, I know that's going to end up being a circle. Okay, and I know if I want to find the area of a circle, what we do is we do pi r squared or pi d squared over 4. Okay, so the area of a circle, again, is either pi r squared, we all know that, or we know that the radius of a circle is equal to half of the diameter. So if I wanted to write this differently, instead of writing area as pi r squared, I can say that also equals pi d squared over 4. Because remember, the radius is half the diameter. So if I do radius squared, I do the diameter over 2 squared, which gives me the diameter squared over 4. So I'm given the diameter here, so that's why I want to use this equation. So what I'm going to do now is I'm going to multiply by its cross-section area, which is pi, times by its diameter squared. Its diameter is 250 times 10 to the negative 6, because it's micrometers, squared, over 4. And we're dividing all that by its length, and its length was 2 meters. So all we have to do now is plug that data into our calculator. So I'd probably do this first. So I'm going 250 times 10 to the negative 6. I'm going to square that number. I'm going to multiply by pi. I'm going to divide by 4 to get what my cross-sectional area is. I'm going to multiply by the resistance, which is 0.5. And we're going to divide by the length, which is 2. And when we do that data, we're going to get a resistivity of 1.23 times 10 to the negative 8. Okay, if we want to find what the units for resistivity is, we did a resistance, which is in ohms, times an area, which is a meter squared, divided by a length, which is in meters. So hopefully you can see a meter squared a meter, it's going to cancel to leave me with an ohms per meter.